The National Air and Space Museum has two wonderful examples of long-distance aircraft, both designed by Burt Rutan, the well-known designer of sophisticated, different, game-changing aircraft. The Voyager he designed in the 80s, and that was the first plane to fly nonstop, non-refueled around the world in 1986. And it's based on the high aspect ratio glider wing. So it's thin wings that will glide through the air with less drag. They're long and thin, and they really just slice through the air very nicely. It's got a pusher and a puller engine, and then it's got the flying fuel tank aspect to it, which is you have to carry all the fuel with you. So that's designed around the cabin, along the wing of the airplane, in kind of a catamaran configuration. Then a few years later, someone decided to do it with a jet engine, and Burt Rutan decided that he would take the original Voyager design, add a jet engine to it, and then Steve Fossett successfully flew that design around the world in 2005, breaking all the earlier Voyager records. Round-the-world flights were nothing new. People were always trying to break a record there. What was significant about the Voyager and the Global Flyer flights is that they were the first non-stop, non-refueled flights around the world, which means they carried all the fuel with them in their fuselage.
In 1986, the Rutan Voyager became the first aircraft to fly non-stop around the world, a distance of over 26,000 miles. And some of the longest-range commercial aircraft can fly well over 8,000 miles non-stop, while requiring only 2 miles of runway length. That's an enormous ratio when you think about it, over 4,000 to 1. Now, the route that an aircraft takes to fly point to point on the Earth's surface is not a straight line when viewed on a map projection. We have to think of the shortest distance in three-dimensional space, where the shortest distance is called the Great Circle Path. If this straight line is projected on a map, then we see the grand arc that's formed by typical flight paths across the globe. In some cases, particularly between North America and Asia, the shortest path takes the aircraft over the polar regions of the Earth. When traveling by land, we would think long and hard about a route passing over a polar region due to the harsh environment present there. However, in an aircraft, the air environment is roughly the same, making the harsh nature of the terrain below nearly irrelevant. This makes for some fascinating views for those fortunate enough to grab a window seat. While the Great Circle Path provides the minimum distance, it doesn't necessarily provide the minimum flight time or minimum fuel burn. The winds aloft will have a huge impact on which path is shortest or most efficient. One wonderful example of this is Air India Flight 173, which flies from New Delhi to San Francisco. The Great Circle Path is 7,706 miles. Not the longest flight out there, but certainly a long haul. Air India had been flying the Boeing 777-200LR on a polar route that was close to the shortest path, with one particular flight along this route traveling 8,264 miles. However, they changed the routing to fly over the Pacific instead, adding over 600 miles in the process. While the aircraft flew much greater distance, they shaved between 1 and 3 hours off the flight time. The difference wasn't due to some kind of time warp over the Pacific Ocean. Instead, the flight planners and pilots relied upon the consistent position of the jet stream over the Pacific Ocean, flowing from west to east. The winds in the jet stream can be incredibly strong, well over 100 miles per hour, which gives the aircraft a substantial push as it flies eastward. The strength of wind, whether a headwind or a tailwind, has a huge impact on nearly every flight. Transcontinental flights in the U.S. flying eastward typically have much shorter flight times due to the prevailing winds. And pilots are always concerned about what the winds are, with an eye towards planning for the winds to ensure that enough fuel is on board. This thinking pervades the pilot community to such an extent that a common expression of well wishes is blue skies and tailwinds. Designers and pilots need a reliable way to predict the performance of their aircraft. An accurate calculation of range is critical for several reasons. The airlines care a great deal about whether an aircraft they buy can reliably fly long-haul legs, such as New York to Singapore, nonstop. If the aircraft manufacturer promises a particular range or city pair for the airline, they had better be able to deliver on that promise. Stiff fiscal penalties are written into the contracts if the aircraft can't deliver. Pilots also need to be able to calculate the range of the aircraft very accurately. They need to know how much fuel to carry on board. Because if you run out of fuel in your airplane, you can't just pull off to the side of the road. You have much fewer options. So let's develop the methods that designers and pilots use to estimate the range of an airplane. We'll start with a propeller-driven airplane, and then extend the same ideas to jet aircraft. The fundamental equations for determining the range of propeller and jet aircraft are different from one another, because the performance limit on an internal combustion engine is maximum power, while the limit of the jet engine is thrust. For maximizing the range of a propeller-driven airplane with a fixed amount of fuel on board, we need to minimize the burn rate of fuel per mile. This is really the same idea as maximizing the mileage of your car, which is expressed in miles per gallon. In this case, however, we are considering the inverse of that situation. Our goal here is to minimize pounds of fuel burned per mile. However, the aircraft engine's fuel economy isn't rated in pounds per mile, since the engine can't know how far it has traveled. Instead, the engine's fuel economy is rated in pounds of fuel per hour, per horsepower. That is, at high power settings, the engine will burn more fuel per hour than at low power settings. So we normalize the fuel burn rate by the engine power setting. This parameter is called the specific fuel consumption, or SFC, and has units of pounds per hour per horsepower. Considering the units of specific fuel consumption, we see that we need to somehow express fuel burn in terms of pounds per mile instead of pounds per hour. The link between the two, of course, is airspeed. If aircraft is flying faster than for the given specific fuel consumption and power setting, then it will cover more ground in a given amount of time. A typical value of SFC for a general aviation aircraft engine is about half a pound of fuel per hour per horsepower. This gives a fuel consumption of 60 pounds per hour, or about 10 gallons per hour, when the aircraft is cruising at a power rating of 120 horsepower. If an aircraft is traveling at 140 knots, which is about 160 miles per hour, with a fuel burn of 10 gallons per hour, this gives a fuel economy of about 16 miles per gallon. That's a pretty favorable comparison to a SUV, especially considering that the airplane is cruising at about 2.5 times highway speed and can take the shortest point-to-point route. So let's bring these three parameters together: specific fuel consumption, power, and airspeed, and consider how we can optimize the range. We need to minimize the specific fuel consumption, minimize the power setting, and maximize the airspeed, all at the same time. Specific fuel consumption is relatively constant for a particular engine. It varies a little bit with power setting, but not by much. So once the engine for an aircraft is specified, the value for the specific fuel consumption is set. When operating an aircraft, however, the power setting and airspeed can be set by the pilot. It turns out that the speed with minimum drag is an optimum flight condition for maximizing the range. To see why this is true, we can combine the engine power setting and velocity into a single ratio of power required over velocity. Based on definition, the power is equal to thrust times velocity. So the ratio of power to velocity simply becomes thrust. And in steady level flight, the thrust must equal the drag. So for maximizing the range of a propeller aircraft, we need to minimize the drag. Now, this minimum drag airspeed occurs when the induced drag and the parasitic drag are equal. And since this minimizes drag, this is also the condition for maximum lift-to-drag ratio. So we see that the aircraft designer needs to maximize lift-to-drag ratio, and position that optimum condition near a suitable airspeed for cruise. And if the pilot wishes to minimize fuel burn per mile to stretch out the maximum range, then the airspeed for maximum lift-to-drag ratio should be flown. The airspeed for L/D max is typically well below the maximum speed of an airplane, and even well below the normal cruise speed. If maximizing fuel economy and extending the range are of paramount importance, then it will take longer to get to the destination than if the pilots flew at normal or max speed. Let's now pull these ideas together into one equation, which is the Breguet range equation for a propeller-powered airplane. The propeller efficiency, eta, is included since it represents how much power from the engine is actually transmitted to the air for the purpose of propelling the aircraft forward. Typical values of prop efficiency are about 85%. We see that the natural log of the ratio of initial to final weight is also included in the range equation. The difference between initial and final weight, of course, is the amount of fuel that is burned in flight. The higher this ratio is, the more fuel is carried on board, and the longer the range will be. The maximum amount of fuel that can be carried on board is limited by maximum total weight of the aircraft, which figures into other important design criteria, such as structural loading, stall, and takeoff distance. Also, when we examine the weight ratio from a designer's perspective, we see that it is best to minimize the weight of the aircraft relative to the fuel weight. The ideal case would be an extremely lightweight aircraft that could carry as much fuel as possible, of course. The Rutan Voyager's total weight, most of which was fuel, was 4.3 times its empty weight. For typical single-engine general aviation airplanes, the total aircraft weight is about 3,000 pounds, with a full fuel load of 360 pounds or so, a fuel fraction of only 12%. And if an aircraft designer or pilot wishes to extend the range of an aircraft, the best way to do so is by increasing the fuel load on board. Extra fuel tanks can be installed, taking care not to change the center of gravity of the aircraft beyond safe limits. This is exactly what Jerry Mock did when she became the first woman to fly solo around the world in 1964. Jerry was a native of Ohio and one of the first female aeronautical engineering students at Ohio State University near the end of World War II. Later, as a private pilot and bored housewife, she decided that she needed more adventure in life. So she decided to set out on her circumnavigation flight to learn more about the world around her. It was only after she started planning her flight that she realized that no woman had yet flown solo around the world. Almost 30 years prior, back when Mock was 12, the famous Amelia Earhart had made her own famous but fatal attempt in 1937. In both cases, it was necessary to modify a standard aircraft so that it could carry more fuel. What Jerry Mock did was move 3 of the 4 seats of the Cessna 180 she co-owned with her husband. While the standard Cessna 180 has a range of only just over 1,000 miles on 55 gallons of fuel, Jerry loaded the aircraft with an extra tank in place of the seats in order to add 183 gallons of fuel capacity and extend the range to a whopping 3,500 miles. With that extra equipment, she launched her attempt from Columbus, Ohio, on March 19, 1964. She was able to successfully fly her little Cessna 180, the Spirit of Columbus, through exotic locales including Casablanca, Tripoli, Cairo, Dhahran, and Guam. One of the last legs of her journey took her from Honolulu, Hawaii, to Oakland, California, a distance of over 2,400 miles. She ultimately came back to Columbus for a heroine's grand welcome on the night of April 17th, just 29 days later. Clearly, her extra fuel tanks were a must for transiting over the vast expanses of ocean that she covered. So, for maximum range of a propeller aircraft, we need to maximize the amount of fuel carried on board, maximize the propeller efficiency, have an efficient engine on board that minimizes specific fuel consumption, and fly at the airspeed for maximum lift-to-drag ratio. Note that range is a nonlinear function of aircraft weight, where each additional mile of range performance requires a little bit more fuel than the previous mile. This is because the overall weight goes up as more fuel is carried, and a heavier aircraft will burn more fuel. This is the reason that aircraft typically fly with only the amount of fuel needed for that particular flight. The fuel requirements are dictated by FAA safety requirements or the airline's internal policy on how much fuel reserve is required for a particular flight and under the current weather conditions. Poor weather conditions increase the risk of a diversion, so increased fuel reserves are required for those flights. Pilots will plan on the required fuel for the flight using performance data from the manufacturer, which is very closely related to the estimates that we can come up with via the Breguet range equation. Let's now turn our attention to the range of jet aircraft, which follow similar behavior as propeller aircraft, but encounter different constraints. The main difference is that jet engines are rated in terms of maximum thrust performance, rather than power limitations. This difference affects how the equations are developed for optimum range. This form of the Breguet range equation is for jet aircraft, with an assumption of constant speed. Now, at high flight speeds, it's more convenient to hold Mach number constant, since that is what actually is measured in the cockpit. Conveniently, the air temperature is constant in the stratosphere where airliners cruise, so the speed of sound is constant. Thus, Mach number, speed of sound, and airspeed may all be considered constant in the stratosphere. The reason that we wish to hold the Mach number constant relates to the constraints of air traffic control. It is much easier for ATC to maintain separation between aircraft when they are all flying at about the same speed. So aircraft will all fly at about the same Mach number, between about Mach 0.82 and 0.85. This form of the Breguet range equation, with a constraint of constant Mach number flight, shows that we want to maximize the lift-to-drag ratio, minimize the specific fuel consumption of the jet engines, and again maximize the difference between initial and final weight. But as the jet aircraft burns fuel, its weight decreases, and we must maintain lift equal to weight for equilibrium flight. So the lift produced by the aircraft must go down throughout the flight. Since we're now constraining Mach number to be constant, and we need to maintain maximum lift-to-drag ratio, our only option is to allow density to vary. As the aircraft weight decreases, we have to allow the aircraft to climb to lower density at higher altitudes in order to maintain optimum flight conditions. Ideally, a pilot would put the aircraft into a gradual and continuous climb where the loss of lift with the decrease in density would equal the loss of weight due to fuel burn. This is what is called a cruise climb, a gradual climb in altitude in order to maintain conditions for best fuel economy throughout the flight. The only problem with the cruise climb is the congested flight environment that air traffic control must manage. In this constrained environment, aircraft are cleared for specific altitudes or flight levels that they must maintain in order to ensure sufficient vertical separation between aircraft. In an effort to maintain this structured environment, but still offer fuel savings to the airlines, air traffic control will periodically clear aircraft to higher flight levels. This type of compromise is known as a step climb. To give an indication of how often a step climb might occur, let's consider a Boeing 747 in cruise conditions, where it burns around 4% of its total weight in an hour. So the density would have to decrease by 4% in that same hour in order for the jet to stay at optimal cruise conditions. This equates to an altitude change of about 1,000 feet per hour of flight. By the way, while we're talking about the fuel burn of a Boeing 747 in cruise, let's contemplate the staggering numbers involved. The combined fuel burn for the 4 engines on a 747 is 1 gallon per second, which for a 10-hour flight is 36,000 gallons, or 238,000 pounds of fuel burned. The aircraft cruises at a rate of roughly 1 mile every 5 seconds, giving a fuel burn of 5 gallons per mile. This is a measly 0.2 of a mile per gallon. That sounds horrible compared to the most fuel-efficient cars out there, which might have a fuel economy of 40 miles per gallon. But wait, that comparison is not exactly fair. A typical American car carries only 1.5 occupants on average. If we define a metric of fuel burn per person, then we're doing a much better comparison. We'll express this in terms of person miles per gallon. In this case, the car with 2 people at 40 miles per gallon achieves a normalized economy of 80 person miles per gallon. But a 747 can easily carry 500 people, achieving a normalized fuel economy of 100 person miles per gallon. On top of that, the 747 travels at a speed nearly 10 times faster than an automobile and can easily traverse inhospitable terrain. So aviation really can be reasonable in terms of fuel economy. For a propeller-driven aircraft, about 12% of a typical general aviation aircraft's maximum weight can be in fuel. In contrast, the fuel fraction of a commercial airliner is simply stunning. Long-range jet aircraft can have a fuel fraction approaching 50%. For example, the weight of a fully loaded Boeing 747-8 is 987,000 pounds, and the fuel weight is 416,000 pounds. That's a huge change in weight over the course of a long-haul flight. Despite the fact that an airliner can carry that much fuel, remember that aircraft will usually carry only what they need for that flight. So before every flight, the pilots have to carefully calculate, usually through the flight computer, how much fuel they should have on board, considering contingencies such as winds aloft and the possibility of a diversion. In one case, the pilots didn't crunch their numbers as carefully as they should have, and the consequences were dramatic. On July 22, 1983, Air Canada Flight 143, a Boeing 767-200, was preparing for departure from Montreal, bound for Edmonton. The flight took off and proceeded westbound at an altitude of 41,000 feet and 469 knots. About halfway through the flight, however, the pilots received a warning of low fuel pressure on the left engine. Unaware of the true problem that they faced, they proceeded to shut off the fuel pump, allowing the fuel to feed the engine via gravity. Then, a second warning sounded for the fuel pump on the right side. At this point, the pilots recognized the escalating situation. They shut down the right fuel pump and decided to divert to nearby Winnipeg. As they were coordinating with air traffic control for the diversion, suddenly the left engine flamed out. They attempted to cross-feed fuel from the right tank to the left engine and began preparations for a single-engine landing. Just a couple minutes later is when things got really serious. The right engine also flamed out, and the cockpit sounded a long, audible warning that the pilots had never heard before, not even in training. Their high-end 767 with computerized flight management system was now a 132-ton glider with no power other than limited battery backup and a reduced set of instruments. They had run out of fuel. This was a nearly unforeseen occurrence. The pilots had never trained for this event, and the flight manual did not have instructions for an emergency with complete loss of power. The pilot attempted to fly the aircraft at what he estimated would be the best glide speed, 220 knots. As they projected ahead, making calculations of their sink rate and glide path angle, they began to realize that they would not make it to Winnipeg. The co-pilot, having come from a military background, recalled a nearby former Royal Canadian Air Force base in Gimli, Manitoba. So they made their way to Gimli. What the pilots didn't know was that one of Gimli's runways had been converted into a racing park. And that very day was a large racing festival with many people camping and recreating on and around the decommissioned runway. As the captain glided the aircraft towards this closed runway, he noticed all of the people and activity on the runway. But it was too late. He was committed to land on that runway, and there was no other options. Miraculously, he was able to bring the aircraft to a stop in less than 3,000 feet, and just short of a large crowd of stupefied onlookers. Everyone walked away from the incident, with the worst injuries being minor ones encountered during the emergency evacuation. So, what exactly led to the fuel exhaustion of the 767 that is now known as the Gimli glider? Well, it turns out that it was a comedy of errors, including faulty fuel gauges and human factors. The pilots and ground crew had to manually calculate the fuel requirements for the flight. However, the 767 was new to the Air Canada fleet, and the airline was still in the process of switching units for the systems of measurement. The pilots relied upon an English conversion factor for converting between fuel volume and mass, when their flight computer was expecting the data in metric units of kilograms. This led both the pilots and the ground crew to miscalculate how much fuel would be required for the flight. They ended up with less than half the required fuel, despite many checks and rechecks. So, as is obvious here, an aircraft can't simply pull off to the side of a road in the event of fuel exhaustion. Instead, the pilots have to quickly hunt for a suitable place to land. Let's now turn our attention to the other key distance in flight that we have to worry about: runway length. When a pilot is preparing to take off from a particular airfield or planning a flight to a distant airport, one of the most critical assessments to be made is whether the runway length is suitable for the airplane. Runways across the U.S. can vary dramatically in length, anywhere from a short grass strip of less than 1,000 feet to the 16,000-foot runway at Denver International. So how is a pilot supposed to decide between what is safe and unsafe? Well, we can do some analysis to predict the takeoff performance of an aircraft, which is what engineers do in the aircraft design process. The required runway performance is a combination of the ground roll plus the lateral distance to climb to an altitude for obstacle clearance, which the FAA defines as a 50-foot obstruction. This analysis starts with Newton's second law, stating that the net force acting on the aircraft is equal to the product of the aircraft mass with the time rate of change of airspeed. The forces acting upon the aircraft are thrust, drag, and the rolling resistance of the wheels on the runway surface. It's important to point out that these forces are not constant. Instead, each one is a function of airspeed. The thrust will be mostly constant, but will vary a little bit depending on the difference in inlet and exit velocity for the engine. Aerodynamic drag, of course, scales quadratically with airspeed. And the rolling resistance is equal to the coefficient of friction between the wheel and the runway surface, times the downforce acting on the landing gear. This downforce is the difference between weight and lift. As the aircraft accelerates and lift continues to build with the square velocity, the wheels become unloaded until the aircraft leaves the surface. So we have force as a function of airspeed on one side of the equation and the time rate of change of airspeed on the other side. This is a classic first-order differential equation, which needs a little extra work to solve than relying on algebraic manipulation. We could enter this equation into a computational solver that works through the solutions using small finite time steps. Or we can rely on some average values of the thrust, drag, and rolling resistance forces acting on the aircraft. Taking the latter approach and integrating, we can come up with a distance for the takeoff roll. With this equation, we'll also assume that the thrust is much greater than the aerodynamic drag and rolling resistance. This is not an entirely accurate approach, but it does allow simplification of the resulting equation, which clarifies the key factors that govern takeoff length. First, we see that the square of the aircraft weight appears in the numerator, indicating that the weight has a very strong impact on the takeoff length. Second, since the density appears in the denominator, we can note that low density will increase the takeoff length. And finally, to minimize takeoff distance, we should maximize wing area, maximize lift coefficient, and thrust, all of which appear in the denominator. Also, if we group together aircraft weight with wing area, we see that the wing loading should be minimized for optimum takeoff performance. However, once the aircraft design is set, the pilot typically has little control over these values, except in the selection of flaps for changing the lift coefficient. So, for a pilot operating an aircraft, the primary concerns for takeoff runway length are weight and density. A heavy airplane operating in low density on a hot day at high altitude airport will have a very difficult time taking off. Hot, humid, high, and heavy are traits that make flight more difficult. The effects of density are precisely why Denver has the longest runways of any airport in the US, because Denver is also one of the highest altitude large airports. I experienced these density limits on takeoff performance firsthand when I was learning how to fly at the US Air Force Academy Airfield. With a field elevation of over 6,500 feet and a runway length of only 3,500 feet, I would often encounter the limitations of takeoff performance. On a typical summer day, it didn't take long for the temperature to rise to a point just in the low 80s where the density would drop low enough that the performance of the aircraft would be unsuitable for the runway. The required takeoff distance quickly edged past the limits of the airfield, and we would have to wait for another day. So there were many days where I was grounded due to the density altitude limitations on the takeoff distance. Let's now pull together the physics of aircraft range along with takeoff performance to see how both of these played a pivotal role in a defining moment of World War II. The sudden bombing of Pearl Harbor on December 7, 1941, left the U.S. unprepared and scrambling to put together an effective response to the Japanese attack. The U.S. military needed someone to design, coordinate, and mastermind an audacious counterattack on Tokyo, forming a surprise strike at the heart of the enemy. They turned to none other than Jimmy Doolittle, who had spearheaded instrument development for blind flying. Doolittle exhibited the courage, tenacity, and intelligence needed to pull this mission off. He assembled a team of the top-rate pilots and began planning the counterattack mission in earnest. The idea was to load the aircraft carrier USS Hornet with B-25 aircraft for a bombing run on Japan. The B-25 bomber was too large to be able to return to the aircraft carrier, so this would be a one-way mission with landing in China. Doolittle's first challenge was to modify the bombers and eke out every last bit of performance for them to take off from the limited confines of an aircraft carrier deck of only 824 feet. This is well beyond the original design specifications of the B-25. The second critical issue was to carefully plan the range and fuel requirements to determine the location in the Pacific where they could launch the attack and still make their way to safety in China following the bombing run. As the Hornet was sailing westward in the Pacific towards Japan in April 1942, they spotted a Japanese aircraft nearby and feared that their clandestine mission would be exposed. So Doolittle made the critical decision to launch the mission early. He himself took the bold step of piloting the first aircraft to launch from the deck. This was the most limiting case since the deck of the aircraft carrier was crowded with the other B-25s, leaving little room for a takeoff roll. Doolittle successfully launched, showing that it could be done, and led the way for 15 other B-25s to follow. Immediately following his mission, Doolittle was incredibly downcast because not a single aircraft had made it to a successful landing due to a lack of sufficient fuel. However, the raid on Tokyo had gotten through and was an incredible boost to morale for the American public and set the U.S. on a path towards ultimately winning the war. Instead of being court-martialed, as he feared, Doolittle was welcomed home as a hero, ultimately being awarded the Medal of Honor. And this seminal moment in World War II could not have been executed without a careful understanding and analysis of aircraft range and takeoff distance.